Hello students, very warm welcome in this beautiful series of GATE PYQ of aerospace. So I hope your preparation is going absolutely fine and everything is perfect. So today we are going to discuss the previous year questions of aerospace branch. As far as thermodynamics is concerned, if you go and check, then from basic thermodynamics, if you see, the number of questions that asked was is less compared to other subject. That is true, but this is as a basic subject. So whenever you are going to learn other subjects like uh, jet propulsion or applied thermodynamics or even fluid mechanics, aerodynamics, correct. So in these subjects there is a use of energy balance, there is a use of, like, you will study isentropic efficiency, what is entropy constant means. So these things are there, even combustion systems, combustion of fuel, Brayton cycle. So these are the basics topics are going to be covered in this subject thermodynamics, that is a basic concepts. So if you see, every year 2 to 3 questions were asked from this particular subject, 2 to 3 questions, and the weightage is hardly 4 to 5 marks only, right? The weightage is 4 to 5 marks, and but the point is this subject is very much important and you need to solve the problems of this subject very well, because if you are not good in thermodynamics, it is going to be very much difficult for you to cope up with applied thermodynamics, to cope up with jet propulsion, or even little some part of aerodynamics also required the concept of energy balance. So if you are good in energy balance, entropy, combustion, then definitely it will give you an edge. The one very important point I would like to share here, that uh, these questions are going to be very important as prospective of, like, say it is 4 to 5 marks, that is fine. It's not about the marks, it's about that most of the students who are preparing well, right? The students who are preparing well, the students who are studying well, so they are going to solve these problems because the problems are very easy. So there are two type of things that you need to remember always. The very first thing, there are some questions in a gate paper that are called as rank deciding questions, and those questions are not going to affect your selections, correct? For example, let's take, there is one very difficult topic, right? And if a very difficult questions comes from a very difficult topic, then majority of students are not able to solve. Let's say 99, even some topics are there through which even more than 99% students are not able to solve. Only few students will able to solve that problems, and they are going to convert these marks into the rank, and they will get top 10 rank, top 20 rank, like that, right? But let's say one very simple questions were asked from very simple topic, and some 60 70 people are going to able to solve that problem, but you are not able to solve. Why? Because you left that topic. In that case, that will affect your selection, not only rank, that will you will not even get a top 100 rank, because the majority of the people who are average student compared to you, they might be average, but still they got better rank than you because they did not left any simple part. So as far as this subject thermodynamics is concerned, it is a very simple subject, very basic subject. The questions that would see in mechanical perspective, if you see mechanical engineering, it is a core subject. So in mechanical perspective, if you see, this is a very difficult as well as very important subject. Even mass perspective, the 12 marks are being asked from the thermodynamics as far as mechanical branch is concerned. But in aerospace, hardly 4 to 5 marks are going to be asked from this particular topic. And even though the questions level is going to be little bit easier compared to mechanical, easy questions will be there, but at the same time these are going to decide your selection, because if you left these questions, right, then even average student will able to solve, and it may create the problem for you in to get a good rank. Okay, so there are some people who are saying, okay, I am from NEET. Hey, no NEET, why? It is a GATE. That is for GATE, not for NEET and aerospace. Okay, very good evening Deepak, very good evening विश्वजीत. शिवम सर, अभी मैंने ही फ्लूइड मैकेनिक्स कंप्लीट किया है, पाइप फ्लो, नेक्स्ट शुड आई स्टार्ट थर्मल? यस, डेफिनेटली यू शुड स्टार्ट, definitely you should start. Very good. So let's begin with the very first question, right? Begin with the very first question, right? This is based on the combustion and thermochemistry, right? So in this question, if you see, the combustion between the fuel octane, that is given as hydrocarbon, that is C8H18, and the oxidizer is air, occurs inside the combustion following is a stoichiometric chemical reaction, right? I hope you are able to know, you are already know about stoichiometric chemical reaction. Stoichiometric chemical reaction means the air which is sufficient amount of air that is required to burn the complete hydrocarbon, whatever fuel is there, completely it is going to burn, and there is no any excess amount of air is remaining, exactly the minimum amount of energy that is required. Okay, now in this, so this is the stoichiometric equation is written here. The atomic weights of hydrogen, oxygen, nitrogen are given, even we know about it. If the combustion take place with the fuel and air, so here the combustion take place with the fuel to air ratio. So fuel to air ratio, actual fuel to air ratio, if I say actual fuel to air ratio, yeah, this is actual basically, right? Actual fuel to air ratio is basically given as 0.028, 0.028, correct? This is the actual fuel air ratio is given, correct? Oh, very good, very good. Who is giving the answer? Deepak, very good, congratulations. Now they are saying that what is the equivalence ratio? Phi they are asking, equivalence ratio they are asking, phi. So we already know that phi is basically what? Phi is basically the fuel air ratio actual to the fuel air ratio of stoichiometric, right? So fuel air ratio of stoichiometric. So this ratio is basically called as the equivalence ratio, that is 5. Khush rahiye. Pranipat, you can say good evening also, that will be fine. It is an English channel. In English channel you are saying Pranipat sir, okay. Now so we need to find out what is the fuel air ratio of stoichiometric mixture. So if I calculate the fuel air ratio of stoichiometric, so in that case you can see from the equation here, to burn the 2 moles of C8H18, right? Here you can see that the 2 moles of C8H18, 25 moles of oxygen is required and 24 moles of nitrogen is required, and this is called as the air, right? This like oxygen and nitrogen mixture is going to called as the air. So what is the mass of, like I would write here, mass of the fuel to the mass of the air in stoichiometric equation. So what is the mass of the fuel? So 2 times of 2 moles of C8H18. What is the mass of C8H18? It is very, very easy, right? C carbon is given as 12. So 12 into 8. 8 carbons are there, right? 8 carbons are there, and the atomic weight is given as 12. So this is 12 into 8 plus 18, like 1 into 18, I would say 1 into 18. So this is the mass of the fuel. Now what is the mass of the air? Mass of the air, if I write then I can say that 25 O2. O2 is how much? Actually O is 16. So O2 is going to be 32 plus 94 times of N2. N2 is how much? 14, n is 14, so it is 28. So if I calculate this, I have calculator with me. Very good, very good. So we have I have calculator with me. So 12 into 8 plus 18 into 2. Okay, so this value will come 228 divided by 25 into 32 plus 94 into 28. So this value will come 3432. So from here, if you calculate fuel air ratio, 228 divided by answer, if you say, you will get 0.06643, something like that, right? Now we have to calculate the actual fuel air ratio is already given, that is 0.028, and the stoichiometric fuel air mixture is basically 0.06643, like that, right? So this value will come 0.028 divided by answer. If you do, you will get a 0.4214. So this is going to be your answer. This is going to be your answer. So which one is going to be the correct answer? B we can approximate as a correct answer. So I hope it is you people are able to understand. Deepak. Okay, shall we proceed to the next problem? Shall we? This problem was asked for 2 marks. You can see it is a very simple problem. That's what I'm telling you, Deepak, right? That's what I'm telling you, students, that the questions might be easy and the questions might be there is chance that these type of question may not come every year, but if the question will come, then it is going to decide your selection. Okay, because 2 marks and such a simple problem. Okay, let's move on to the next problem. Now this is our next problem based on the combustion in the, that is also 2 marks question. If you see 2 marks question asked for 2008. Air enter in a combustor of gas turbine engine on at a total temperature of 500 Kelvin. No, it is here some typing mistake may be there. Air enters the combustor of gas turbine at a temperature of, at inlet, it is actually inlet, I hope so, at the inlet temperature of, inlet temperature of 500 Kelvin and leaves the combustor at total exit temperature of 1800 Kelvin. Might be total, but total temperature does not have any sense. That's what I'm thinking. Okay, temperature 80. If the Cp remains constant, Cp value is given, and heating value of the fuel is 44 megajoule. The fuel air ratio, right? We need to calculate fuel air ratio. See, basically it will be look like this one. Suppose this is a combustion chamber. Let's say, assume that this is a combustion chamber. Now in this combustion chamber, air is basically entering. What is entering, beta? Air is entering. Let's say mass flow rate of air is ma dot. I'm writing ma dot, right? Mass flow rate of air entering is ma dot, and it is entering at condition of 1. 1 means 500 Kelvin, right? It is entering at a 500 Kelvin. Okay. Now from in this combustion chamber, we are supplying some fuel. We are supplying some fuel. We are supplying some fuel at the rate of mass flow rate of the fuel, mf dot. Finally combustion will take place, and we will get ma plus mf, ma dot plus mf dot at condition 3, or 2, sorry, not 3, 2. And at point 2, what is the temperature? At point 2 temperature is 1800 Kelvin. Here temperature is given as 1800 Kelvin, right? Now if I apply here the energy balance, right? If I apply here the energy balance, my dear student friends, energy balance in the combustion chamber, then the energy which is entering to the combustion chamber through air, right, that can be written as ma dot cp t1, because actually it is enthalpy H, right? And I already told you for any ideal gas we can write it as a dH is equal to Cp dt, mCp dt. dH can be written as a mCp dt with the help of absolute temperature. At absolute temperature, if we are considering enthalpy as a 0, so in that case the energy at point 1 can be considered as mCpt, can be considered mCpt. So I can add MaCpt1 plus how much energy we are adding basically due to combustion, that is mf into calorific value, right? So mf dot into calorific value into efficiency of combustion also there, right? Efficiency of combustion means what? Means what is calorific value? Calorific value is the amount of heat which is released due to complete combustion of the fuel. So if the fuel is going to, like, let's say 1 kg fuel you have, if you burn the 1 kg fuel completely, then 44 megajoule amount of heat is going to be produced for 1 kg combustion. But if suppose some 5% fuel is not burned, there may be chance. So efficiency of combustion in that case would be 0.95. But in the question, if there is nothing is mentioned about efficiency of combustion, in that case we will consider it as a 1. Correct. So this we will consider as a 1, that is equals to Ma dot plus Mf dot into Cp. Now it is given that it may be Cp of exhaust gases, but actually it is given that the Cp remains constant. Cp is not changing, so I am writing Cp itself, right? And the T final is T2, right? So this is basically our energy balance equation, where we will consider it as the, like, this value will consider as a 100% combustion will consider, okay? Now, but actually what we need to find out, we need to find out fuel air ratio. So do one thing, divide with mass of air, throughout the equation. Here also mass of the air, here also mass of the air dot, here also mass of the air dot. So what you will get? Mass of the air cancel out, so you will get a Cp. Should I write the value also? Should I write the value in this system? Okay, so Cp value is given as a 1.005 into T1 is 500 Kelvin, right? Plus. So this Ma dot and this is going to be cancel out, okay? Now Mf dot by Ma dot, fuel air ratio. That is basically fuel air ratio. This is a fuel air ratio I am writing. Calorific value is how much? So this value will come in kilojoule, correct? Because it is given kilojoule per kg Kelvin. So this also we need to write in kilojoule only. So here it will come 44 into 10 to the power 3 megajoule given a kilojoule. Efficiency of combustion is 1 only. That is equals to, here it will come 1 plus fuel air ratio, right? Fuel air ratio into 1.005 into T2, that is 1300. Just please solve this. Please solve this value. So yes, tell me what is the fuel air ratio that you are going to get? Anyone? Deepak, have you solved like this only and you are getting 0.031, 0.3096? How you got it? I think you are doing some mistake, because there is no such option like 0.3. Okay, so this value will come 500 into 1.005. So this value will come 502.5 plus, now this value will come 44,000, of fuel air ratio, that is equals to how much? That is equals to 1300 into 1.005. So this value will come 1306.5 plus 1306.5 fuel air ratio. So this term will come this side. So minus 502.5, 804. This value is going to come like 804. This value will become 804, and this is going to be minus divided by 44,000. Sorry, 44,000 minus 1306.5. So now you will get here 0.12. You are getting 0.012. How much you are getting? Typing mistake हो गया sir. Okay, so 0.031. How you are getting 0.031? Let me check again. So 1 3 1306.5 minus 502.5, 804 divided by 44,000 minus 1306.5. 0.013, 0.01 something like that, 18 something like that. So that can be approximate. The best possible answer which is near to this is 0.012. 0.012 we can say. The B is coming, right? B is coming or C is coming? 0.188. Yes. So the nearest option we can say B. The nearest option we can say B. Deepak, again you please check. These type of questions I have seen that frequently asked. These type of questions are frequently asked. Oh, sorry. What is there? This is 1800. Huh? Oh, sorry. It is not 1300. Sorry, this is 1800. Okay. I did mistake. Okay. Here 1800 is there. Sorry. So if it is 1800, then it will change actually little bit. Then it will change little bit. Here 1800 is there. Array, this final temperature is 1800. I put 1300 by mistake. By mistake, I put 1300. So this value will become equals to 1800 into 1.005. So this value will come 1809 plus 1809 fuel air. Now is it fine? Now is it fine? Check. So this value will become minus. So minus 502.5. Okay. So divided by 44,000 minus 1809. Oh, Deepak was correct. Fuel air ratio. Fuel air ratio value will get 0.031. 0.031. This is going to be your correct answer. Which one is correct? 3 is C only correct. C is only correct. So I hope you people are able to understand here. Correct. So basically you need to apply energy balance, right? You need to apply energy balance. Once you have applied energy balance, then to calculate fuel air ratio, you have to divide with the mass of the air. You have to divide with the mass flow rate of the air. You will get the correct answer. Okay. Shall I move to the next problem? Okay. Come to this problem. This is based on the first law of thermodynamics. This problem is basically based on the first law of thermodynamics. Here it is given that a piston compress 1 kg of air. Here we have 1 kg of air inside the cylinder as shown. The rate at which the piston does the work. So what is the work done? Work done on the system. So I told you on the system is considered as a negative. So what is the work done on the system? So W is equal to, I can say, minus 3000. Minus 3000 what? Unit is watt. Unit is watt. So this much amount of work is done, right? Right? Okay. At the same time, heat is being lost. Heat is rejected. Heat lost by the system is also considered as negative only. So minus 847.5. So Q value will come. This is W dot, I can say, and Q dot value will come minus how much? 847.5. 847.5 watt. Now after 10 seconds, the change in internal energy, right? After 10 seconds, what is the change in internal energy? So now you need to find out. See, this is a rate of work is given, rate of Q is given, right? So after 10 seconds, right? After 10 seconds, the total amount of work that is going to be supplied, right? The total amount of work is, see, this is a 3000 joule per second we are supplying, right? So this value will come minus 3000 joule per second, and for how many seconds? 10 seconds. So basically this value will come minus 30,000. Yes, 30,000 joule. 30,000 joule of work we are supplying. Similarly, if I calculate Q value, then minus 847.5 joule is required. So this much amount of heat is supplied, this much amount of work is supplied. Now, but they are asking what is the change in internal energy after 10 seconds. Change in internal energy they need to find out. So we'll apply here first law of thermodynamics. What is first law? dq is equal to du plus dw. dq is equal to du plus dw. Now here we are supplying minus 8475. This is the heat transfer, this much joule, then du, and then minus 30,000 work we are supplying. So du value will come how much, beta? Du value will come after 10 seconds, that is 30,000 minus 8475. 8475. So this value will come 21525 joule. 21525 joule, right? So 21525 joule per kg, correct? Acha, 1 kg is given. Okay, no, so mass value is 1 kg only. So here I can write, this can be written as per kg. Okay, dq is equal to du plus dw. So joule per kg, because mass value is given 1 kg only. No problem. Because all this data is given per kg only. All this data is given per kg only, so no problem. So this is going to be your correct answer. This also asked for 2 marks. It is such an easy problem. dq is equal to du plus dw. That's it. It's a very, very easy problem. Okay. Shall we move to the next problem? Okay. 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 Oh my God. So this question is basically for 4 marks. It is a common data problem, right? It is a common data problem. Now they are asking the corresponding change in the temperature of the air. Corresponding change in the temperature of the air. See, in previous one we have find out du value is 21,21521, right? So as we got here, du is equal to 21525, right? 21525, right? 21525 joule per joule, I can say, no problem. Now du value will come how much? We already know for ideal gas du can be written as mcv dt is equal to 21525 joule. Okay. Now then it is given as a 1 kg, so dt value will come how much? 21525. This value is given as 1 kg. So no problem. So divide by CV. Now air is given, I hope so. Yes. For air, CV value is given 717.5. So this value will come 21525 divided by 717.5. 717.5. So divided by 717.5. This value will come 30 Kelvin or degree centigrade, 30 degree centigrade, because in change there is no problem, right? So you can see that this is basically such a easy problem, right? You try to understand such a easy problem, and that too also asks for 4 marks. Let's say one particular student, he did not gone through this subject, right? Only hardly few students will be there who are not able to understand what is the first law of thermodynamics. They don't know, they are not aware of this particular equation dq is equal to du plus dw or du is equal to mcv dt. Then they will not able to solve, and 4 marks difference will come for such a easy problem, right? So I will suggest you that you give this subject as a priority, right? You have to solve all the previous year problem as a priority basis, so that you, because you cannot afford, right? You cannot afford the marks deducted in the thermodynamics, right? Okay, next question. Hot gases, gamma value is given at the temperature. So initial temperature is given, let's say T1 I am writing, right? Hot gases are entering at 400, enter into axial turbine and expand isentropically, right? Isentropic you can consider as a reversible adiabatic. So T1 value is given how much, beta? T1 value is given as a 1450 Kelvin. 1450 Kelvin, enter into axial turbine and expand isentropically. Assume the kinetic potential energy across the turbine is negligible if the ratio of the inlet and outlet pressure, ratio of inlet to outlet, P1 by P2. So P1 by P2 value of the turbine is given as 9.5. P1 by P2 value is given as a 9.5. Then temperature T2 value you need to find out. T2 value you need to find out, right? I have given 3 equation if you remember. For see isentropic, what you can write, beta? Isentropic process can be considered as, can be assumed as, not always, but 99.99999% cases, right? So reversible adiabatic is always isentropic, but isentropic need not to be reversible adiabatic always, but still we can consider it as a reversible adiabatic. Now for reversible adiabatic equation I have given the 3 relations. One is P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Pressure and volume relation. Then next we have given T2 by T1 is equal to V1 by V2 to the power gamma minus 1. And the third and most important one is T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. So this is basically the equation, right? These three equations are there. Any one can be used as per our requirement. So as it is given that for isentropic process, right? Isentropic process means reversible adiabatic. Reversible adiabatic. For reversible adiabatic, isentropic means for reversible adiabatic, we can write here T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. Okay, so T2 value we need to find out. T1 value is 1450 is equal to P2 by actually P1 by P2 is given. So P2 by P1 will be 1 by 9.5. 1 by 9.5 and gamma value is 1.33, so 1.33 minus 1 by 1.33. From here you can calculate T2 value, that you will get directly in Kelvin, and they are asking in Kelvin itself. So what is the answer? Very good. Very good. So 0.33 divided by 1.33, right? So 1 divided by 9.5, the power answer, into 1450. 829 is coming? Yes. So this value will come 829.42. 829.42 Kelvin. Such a easy problem, and that too also for 2 marks. I'm saying it from very long time, like when I started this subject in aerospace branch, when I started this subject, my subject is already over, right, in one particular batch. So in one particular batch of aerospace, I have already completed these topics, right? And at the beginning itself, I said that you cannot afford to leave a single problem of thermodynamics. You cannot afford, because very simple questions are asked, and most of the students are able to solve, you can see. So every year 3 to 4 marks will be asked, but these 4 marks is going to decide your selection. Now come to the another problem. A gaseous mixture of air and fuel enter into the constant area combustion chamber 100 meter per second, and static temperature is given as a 300 Kelvin. So 300 Kelvin, and velocity value is also given. The heat released due to combustion, Q input value is also given, right? The energy entering is also given. If the specific heat at the constant pressure of the calorically perfect gas is 1000 joule per degree Celsius, the total temperature of the air fuel mixture, after the combustion. So after the combustion, what will be the temperature, that you need to find out. Similar problem we have already solved, right? If you recall, you can solve it with the help of what you call very basic equation, that is steady flow energy equation. So per kg, if I apply steady flow energy equation, right? So in that particular case, I can write here H1 plus C1 square by 2000 basically, but actually all these things are given in I will write in joule only or kilojoule. Kilojoule will be fine. Okay, I'll write everything in kilojoules. So C1 square by 2000 plus GZ1, no need to write because there is nothing mentioned about the height and all. So H1 plus C1 square by 2000 plus GZ1 by 1000 plus Q is equal to H2 plus C2 square by 2000. Okay, I'll write the complete equation. GZ1 by 1000 plus Q is equal to H2 plus C2 square by 2000 plus ZZ2 by 1000 plus W control volume dot. Something like that. W controller, not dot, W control volume. Now here if you see, it is a combustion, right? It is simply combustion is going to take place. We are not supplying any external work. At the same time, Z1 and Z2 value is also going to be same because nothing is mentioned about it. Even they did not mention anything about the velocity at the exit. So velocity at the exit also we can consider as a 0 only, right? Velocity at the exit we can like negligibly small, right? We are considering it as a negligibly small. So now it's very fine. Okay, this H1 will take another side. H1 will say another side. So C1 square. C1 value is how much? C1 value is 100 square. Sorry, 100 square by 2000. Everything you have to write kilojoule per kg. Now Q value is heat released due to combustion, means it is going to be added to the system itself. So 1000 kilojoule per kg, right? So this value is 1000 kilojoule per kg is equal to H2 minus H1. H2 minus H1. Now this H2 minus H1 can be written as Cp T2 minus T1. I already told you dH is equal to Cp dt. But Cp value you have to be very much careful here because this value is given joule and all other values are in kilojoule. So I can write here Cp value is 1 kilojoule per kg Kelvin into T2 we need to find out minus T1. T1 value is how much? 300. 300 is equal to, you just calculate this, 100 ka square divided by 2000. This value will become 5. So 1005. Okay. So T2 value will come how much? 1305 Kelvin. 1305 Kelvin. 1305 Kelvin. Arey, very good evening, bhai. Very good evening, Nikhil. How are you? Right? So I hope you are able to understand. This is very, very simple problem. Let's move to the next problem. Okay. Please try to solve this particular problem. Please try to solve this particular problem. In the combustion of gases octane C8H18, the air is to be burned stoichiometrically proportion. Okay. If the air flow rate required is M, like air flow rate requirement Ma dot value. Ma dot value is given as 1 kg%. What would be the corresponding flow rate of octane? Means you have to find out mass flow rate of octane, right? You need to find out mass flow rate of the octane. Okay. So for this, first stoichiometric mixture is there. So for stoichiometric mixture, if I write the equation, so C8H18, right? Now it is going to be burned with the help of air, right? Now air is basically what? Air is, in our case, air is basically O2 plus 79 by 21 times of N2. This is basically the composition of air which we are considering. Actually some traces of CO2, water vapor, all those things are there, but that we are neglecting, right? So this is basically, now I want to convert this, I want to burn this C8H18. So I already told you in the combustion chapter that first what is going to burn? Not coal, because coal at the core of the fuel, right? coal means carbon. Carbon is not going to burn first because the weight, like atomic weight of carbon is more, it is heavy, so it is at the center, and outer periphery in the fuel hydrogen will be there. So hydrogen is first going to burn and it is going to convert into H2O. So first all the hydrogen will convert into H2O. Correct? All the hydrogen will convert into H2O. Okay, fine. Okay, so how many H2O will be formed? This is 18 basically. So here also it should be 18. So 9 H2O will be formed. Correct? Okay. Plus all the carbon is going to convert into CO2, right? So plus CO2. So how many carbons are there? 8 CO2. Now you balance the oxygen. So here how many oxygens are there? 18 2s are 16 plus 9 25. So 25 oxygens are there. Here also 25 means 25 by 2 we can write. Now this equation is basically balanced. Now we have to calculate the flow rate of air, fuel air ratio. Now we will calculate the fuel air ratio. What is fuel air ratio? So carbon is how much? 8 into the mass of the car. I can write like this: mass of the fuel divided by mass flow rate of the fuel to the mass flow rate of the air. I can write that can be, what is the mass of this one? This mass I can write 8 into 12 plus 18 into 1 divided by 25 by 2, 32 plus 79 by 21 times of 28. So now just calculate this. So mass flow rate of fuel divided by mass flow rate of air is equal to, this value will come how much? So 8 plus 8 into 12, 8 into 12, sorry, 8 into 12 plus 18. So this value will come 114 divided by this value will come how much? 79 by 21 into 28 plus 32 into 25 by 2. So this value will come 1716.67. Correct. So 114 divided by answer, if you do, you will get equals to 0.066. Correct, this value. Now mass flow rate of air is given as a 1 kg per second. So 1 kg per second will go this side, and finally you will get mass flow rate of octane, that is fuel, is basically 0.066 kg per second. Wow. Clear, everyone? Everyone, is it clear? So I hope it is clear to everyone. So A is going to be your correct answer. Let's move on to the next problem. Now, the first law of thermodynamics, I told you at the very first line itself, I told that the first law of thermodynamics is basically based on the law of conservation of energy, right? It is first given by the joules for cycle, that net heat transfer is equal to net work transfer for a cycle, and for a process dq is equal to du plus dw. So it is actually a balance of energy. It is actually balance of energy, or it is actually based on the law of conservation of energy. Okay, let's move on to the next problem. Now here, an ideal gas turbine, the expansion of the turbine. See, if you are talking about the ideal gas turbine cycle, what is the ideal gas turbine cycle? That is Brayton cycle. In Brayton cycle, two processes are reversible adiabatic and two processes are constant pressure. So constant 1 to 2 is constant pressure combustion, right? Sorry, compression. 1 to 2 is constant pressure compression. Then 2 to 3 is constant pressure heat addition. Then 3 to 4 is reversible adiabatic expansion. Reversible adiabatic expansion means we can say isentropic expansion. So expansion and compression both are reversible adiabatic. Both are reversible adiabatic. So B is going to be your correct answer. Let's move on to the next problem. A combustor is operating with a fuel air ratio, right? So actual fuel air ratio is given. Actual fuel air ratio is, right, I will write here actual actual is equal to given as 0.03. Now if the stoichiometric fuel air ratio is also given. See how what it is a very easy problem, right? The most easiest problem I have ever seen. They are asking 5. 5 is equal to what? Fuel air ratio of actual to the fuel air ratio of stoichiometric. This value will be 0.03 divided by 0.06, that is equals to 0.03 divided by 0.06. So this value will come 0.5. Okay. Okay. Now solve this particular problem. Now here it is given that for a complete combustion of 1 mole of ethanol. Ethanol, you remember? Ethanol is alcohol only, right? Ethanol, right? So we have 1 mole of ethanol, that is C2H5OH, right? Now they are asking that how many number moles of oxygen is required. Only oxygen they are asking, not air. Oxygen they are asking. So plus O2. How many number of O2 is required? That so stoichiometrically, if we see for complete combustion means stoichiometric only they are asking about, right? So for 1 mole of C2H5OS, how many moles of O2 is required for complete combustion? As I told you earlier also, first all the hydrogen is going to convert into water. So here how many hydrogens are there? Hydrogen atoms are there? 6. So it will form 3H2O. 3H2O will be formed. Then all the carbon will convert into carbon dioxide plus 2CO2. Right. Now see how many oxygens are utilized in during combustion process. So 3 oxygens are this one, and 2 2s are 4 oxygens. So 4, 5, 6, 7 oxygens are basically utilized, right? Now but 1 oxygen is already here in the fuel itself. So how many extra oxygens are required? Only 6. So O2 value will come how much? 3 O2. So basically if you see, the correct answer is basically 3. Correct answer is basically 3. So if you know how to write a stoichiometric reaction, right? If you know how to write a stoichiometric reaction, easily you can write this. Okay. Let's move to the next problem. 1 kg of diatomic gas is heated and its temperature increases from 100 Kelvin to 600 Kelvin. Okay, 100 Kelvin to 1 kg of diatomic. Diatomic means like O2 and 2, right, where gamma value is 1.4. So the energy added at constant pressure during the process. So how much energy we are adding? Q input value is basically given, right? The specific heat value they are asking. So Q is equal to what, beta? Q is equal to beta per kg they are asking. So Cp dt only I can write. Cp T2 minus T1. Now what is the Q input value given? That is 500, right? So Q input value is given as a 500 is equal to Cp. Now T2 value is how much? T2 value is given 600. Final temperature is 600 minus 100. So this value will come 500. Cp value will come 1 kilojoule per kg Kelvin. 1 kilojoule per kg Kelvin. This is the value of Cp. 1 is going to be your answer. Is everything is fine? Correct. Shall I move to the next problem? 1.00. Correct. Okay. come to this problem. This is really a very good problem, I would say. So here they are asking, the figure shows the TS diagram. So pressure here, let's say T01 is given, T02 is given, and this point I can consider as, okay, should I use some little bit easy notations? So this point I'm considering as a 1, okay, fine. This point I'm considering as a 2, and if I go and isentropically, then this is, let's say 2 dash, should I consider? Fine. Or 2s, okay, isentropic. 2s means isentropic, okay, 2 dash is better, I think so, right? So 1 to 2 dash, right? 1 to 2 dash is the isentropic process, and 1 to 2 is the actual process. So the figure of Excel turbine again, assuming that specific heat ratio, means gamma value is basically given. Gamma value is given as 1.33. For the hot gases, the isentropic efficiency we need to find out. Isentropic efficiency. If you remember the isentropic efficiency, what is isentropic efficiency? Isentropic efficiency is basically W actual by W isentropic, right? Isentropic. Now what is W actual? Actual process when we are considering. So this value will come Cp T1 minus T2, right? Cp dt divided by isentropic work. Isentropic was Cp, let's say T1 minus T2 dash. Cp square. So T1 value is known to us actually, right? So I can write a T1 value is how much given? 1050 Kelvin. 1050 Kelvin. T2 value is also given 823 Kelvin, right? 1050 minus. Only T2 dash is not known. Only we need to calculate what is T2 dash. So 1 to 2 dash I am considering as a isentropic expansion, right? Isentropic expansion. So isentropic expansion I can write here like okay, so I will write here T2 dash we need to find out. Okay, so T2 dash by T1 dash T2 dash by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. Just now I have given 3 equations just in previous question, like previous to previous question. I have given the 3 equation for isentropic process. So one equation I'm using. So T2 dash by T1 value is 1050 is equal to P2 value is how much? 2.5 bar. P2 at 2.5 bar and P1 value is 7.8 bar to the power 1.33 minus 1 by 1.33. From here calculate the value of T2 dash. From here calculate the value of it. It is the most simplest way. No need to remember any formula, nothing, no need to remember anything, because most of the time people are remembering the formula. No need to remember, right? Even it is not going to take much time. Here I am explaining, that's why it is taking much time. Otherwise I can solve it within a half minute. So 0.33 divided by 1.33, then 2.5 divided by 7.8, the power answer, right? So into 1050, this value will come 791.734. Okay, so I will consider here 791.373. 791.73. So 1050 minus this 1050 minus 823. So this value will come 0.87894. Correct. So they are asking percentage, so I can write here 87.9% will be fine. Okay. 2 decimal places they are asking. Okay, 87.89. Is it clear to everyone? It's a very simple problem, right? Very simple problem. Okay, come to the next problem. That is, see, you can see that the majority questions are basically like combustion and thermochemistry part. Majority questions were asked. A gas turbine combustor is burning methane CH4. Equivalence ratio is 0.5. And okay, so stoichiometric mass of air. Okay, the air flow rate of is given mass. Okay, so see here what is given. Let me write here. The phi value is given, that is 0.5. What is phi? Basically phi is basically actual fuel air ratio to the stoichiometric fuel air ratio. So basically we have to find out the actual fuel air ratio. If you know the actual air fuel ratio, then problem will be solved. Problem is basically solved, right? So first we'll find out the fuel air ratio of stoichiometric mixture. So how we'll calculate here? See, it is a methane CH4, right? CH4, and what we have air, right? So let's say we have air. So what is air? Air is basically O2 plus 79 by 21 times of N2, right? 79.1 times of N2, right? Acha, one more thing. In some of the question there might be I did not balance the nitrogen because nitrogen is not taking part in the combustion, right? Whatever nitrogen will be there in left side, same nitrogen will be right hand side, right? So this point I would like to share first, right? Because otherwise some people may confuse where this nitrogen gone. For example, this particular question. Because that is not going to affect our answer, right? So here if you see, if I write here right hand side equation, then I can add one more thing like 25, this one how much, 79 divided by 21 into 25 by 2, right? So this value will come 47 point something, 47.02 times of N2. So this type of things will come, but that is not required, right? That is not required. So just for your information, I am sharing that N2 I am not balancing in most of the cases because N2 is not going to affect, right? Even if you say I can write only oxygen also, no problem. Then that is if there is exhaust gas analysis, if I do the combustion products, whatever final products coming out, in that case N2 we must have to consider. Okay, so now what will happen here? I told you first hydrogen will convert into water, so H2O. How many hydrogens are there? 4 are there, so it will be 2H2O plus all the carbon is going to convert into CO2. Nitrogen I'm not writing. So like how many oxygen here utilized? 2 oxygen, 2 of 4 oxygen, so this will become 2, correct? So this is basically our stoichiometric equation. This is basically a stoichiometric equation. So if I calculate fuel air ratio of stoichiometric, so fuel is CH4, so carbon is 12 plus hydrogen is 4 into 1 means 4 divided by 2 into 32 plus 79 by 21 times of 28, correct? So this value will come how much? If you say I can write, no problem, plus 2 into 79 by 21 times of N2. That will not affect, oh, that's it. So just calculate this, 79 by 21 into 28 plus 32 into 2 16 by answer. So this value will come 6 by 103. 6 by 103. So if I put this value here, then from first equation I can say, from this particular equation I can say fuel air ratio actual value will come how much? 0.5 times of this. Let's say into 0.5. So this value will come 3 by 103. That is equals to mass flow rate of fuel to the mass flow rate of air. Now mass flow rate of air is given as a 20 kg per second. So what is the mass flow rate of CH4? CH4, that is sorry, into 20. This value will come 0.5825. 5825 kg per second. Correct? This is going to be your correct answer. Very good. What is your name? Harry. Harry is a good student. Harry seems to be a good student. I hope Harry will get rank this year. And Harry? So Harry, work hard and try to get a good rank. If you get a good rank, then we'll surely meet after GATE exam. And we will together celebrate your victory. Okay, solve this particular problem. Solve this particular problem. For an ideal gas, specific heat at constant pressure, Cp value is given, right? Cp value is given as 1147. Unit is very much important. Joule per kg Kelvin, or kilojoule if you write, then it will be 1.147. Okay. For ideal gas, the specific heat at constant pressure, the ratio of specific heat, gamma value is also given, that is 1.33. What is the value of gas constant for this gas? So gas constant value we need to find out. See, gamma is equal to what, beta? Gamma is equal to Cp by Cv. So 1.33 is equal to 1147 divided by Cv. So what is the value of Cv from here? Cv value you will get 1147 divided by 1.33, right? So you will get 862.4 joule per kg Kelvin, right? Joule per kg Kelvin. Now what they are asking? They are asking the gas constant, characteristic gas constant, that is R is equal to, by Mayer's equation, Cp minus Cv is equal to R. So R is equal to, we can write Cp 1147 minus 862.4. So 1147 minus 284. So this value will come 284.6 joule per kg Kelvin. So A is going to be your correct answer. A is going to be correct answer, Harry. Okay, let's solve this problem. It is asked in GATE 2024 itself, last to last year. The surrogate liquid hydrocarbon fuel, approximately C8H12, right, there is being burned with a liquid based gas turbine combustor with a dry ash compositions are given. How many moles of dry air is required for stoichiometric combustion of, okay, so let's say for stoichiometric combustion or atmosphere, okay, so actually C10H12, right, this is there, right, and plus We basically require what? Air. Air means O2 plus 79 by 21 times of N2, that is equals to. So stoichiometric mixture we want, right? Stoichiometric mixture means what? Right? Stoichiometric mixture means all the hydrogen is going to convert into water. So here how many hydrogens are there? 12. So it is converted into H2O. So it will become 6H2O plus 6H2O. Now how many carbons are there? 10 carbons are there. So it will form 10 CO2 also. It will form 10 CO2. Then how many oxygens are utilized here? If you see, then 6 oxygen atoms and 10 to the 20. So 26 is utilized. So 26 by 2 if you do, then 13 number of 13 number of air is required, and finally the nitrogen if you balance last. So 13 into 79 by 21 times of N2. So finally you can see that how many moles of air is required, how many moles or atom of air is required. So that is 13. So 13 is going to be your correct answer. 13 is going to be, only you need to write stoichiometric equation and 1 marks. Just write the equation and you will get 1 marks free of cost, free. These marks are free marks only. Let's move to the next problem. This is again asked 2024. This is again asked in 2024. So in a air breathing gas turbine engine, the combustor inlet temperature is given as a 600 Kelvin. The heating value of the fuel is given as this one, assuming that Cp value is given, burned air, and the fuel air ratio is much less than 1. Okay, neglect the kinetic potential energy. Okay, so fuel air ratio is very less here given. Correct, fuel air ratio is very less, it is given. So you need not to consider that. You can assume that, well, fuel, the mass of fuel is very less compared to air. So basically you can consider whatever air is entering, approximately same amount of air is coming out. Like that you can consider here. So what is the fuel air ratio, required to achieve 1300 Kelvin? Okay, so see, now in this case you try to understand. Actually you can assume like this, for example, here air is entering, right? Mass flow rate of air is entering, right, in combustion chamber at condition of 1. So here some fuel is also coming, right? Mass flow rate of fuel is coming, but actually at exit I'm writing here mass flow rate of fuel is Ma plus. Should I write Ma plus Ma? No, I'll write Ma only at 3. Now you may confuse, right? You may think of, sir, how you can write here only air, because air plus, right, fuel plus air will come out. Yes, I agree with you, right? Fuel plus air will come out, but it is mentioned that the fuel air ratio is very less, means mass of the fuel is very less compared to air. So that can be neglected. That's why it is given. If it is not, if you consider, then also there will be no much effect in the answer, right? The answer, there will be no much effect. That effect will come after 2-3 digit, after 0.23 digit, right? Then it will affect. So basically we can write here, to simplify this, Ma dot Cp T1 plus Mf into calorific value, efficiency of combustion is also not given, that is equals to Ma Cpa T2. Now it is going to be simplified. Now we'll divide with the Ma both the side. So we'll divide with Ma both the side, Ma both the side. So what you will get here, this is going to be cancelled. This term I am writing another side. So this will come fuel air ratio into calorific value is equal to Cp. Cp value is how much? Cp means this is Cp only. Cp T2. Okay. So Cp T2. Cp value is given how much? the CP of air. Okay, so answer is asked. Okay, either you can write in joule or kilojoule, whatever you want. Should I write in joule? Okay, I'll write everything in joule, right? No problem. So 1100 joule per kg calorie. So 1100 times of T2. T2 final temperature is 1300 minus initial temperature is 600. So basically how much you will get? So finally you are going to get like fuel air ratio into calorific value, that is given as 43.4 into 10 to the power 6, right? That is equals to this value will come how much? 1300 minus 600. There's 700 into 1100. So this value will come 77.2040. So what is fuel air ratio? So divided by 43.4 divided by 10 to the power 6. So you will get 0.0177. So this is 0.0177. So A is going to be your correct answer. Can a mechanical student watch this? You can watch, no problem, right? You can watch, because there are some questions like earlier. From now, I think this topic was removed from your chapter, right? This one. So mechanical student, if they wish, they can watch, because earlier that this thermochemistry chapter, if you see like 2011, 12, 8, 7 questions. So there are even earlier questions. So there are a number of questions which are asked based on the thermochemistry. But in 2018 or 17, that syllabus was revised and thermochemistry was removed, right? So that's why but still if you want to get sure of that, then you can solve, because it's a very basic thing. Oh, so thankfully it is over, right? So these are the basically the question that we discussed related to the thermodynamic, basic thermodynamics. In Monday, we are again planning one session for aerospace. Again, we are planning one session for aerospace. That is basically the PYQs of fluid mechanics or aerodynamics. So PYQs of aerodynamics that I am going to take only, right? So I am going to take one more session where we will discuss the questions related to the aerodynamic part, correct? So I hope Harry will be there, Deepak will be there, and all other people will be there. So everyone is very much welcome in Monday session. So Monday session will be mostly at 7 p.m. right? So that session is going to be at 7 p.m. Here I have discussed about most of the problems. So you have seen that there is one problem based on first law of thermodynamic piston cylinder arrangement. There is one problem which is based on steady flow energy equation. There is one problem, there is number of problems that is based on thermochemistry. There is one problem, even 2-3 problems which is based on this combustion in the gas turbine. Then there is some problem based on isentropic efficiency. There are some problem based on the Brayton cycle, simple Brayton cycle, correct? So these are the key areas through which the question were asked. In last 20 years, whatever questions are asked, whatever topic that the questions were asked, all the topics I have covered here. So I hope this session will be helpful for you. And similarly, I will come with some very good questions of aerodynamics and fluid mechanics and all at Monday. So Monday, be ready with the pen, paper, and obviously calculator, and we'll do a great session, good session in Sunday. So can you also take a session or turbo machinery? If you say, I will take, no problem. Turbo machinery, I think that will be taken by okay, I'll check, right? I'll check, right? If suppose if suppose someone else is taking, I did not gone through that schedule properly yet. So aerodynamic part I'm going to take. If you say, I will add in the thermochemistry also. If you say, I will add some questions of turbo machinery, right? I will add. Basically, there will be session, right? Aerodynamic session is I'm going to take. There will be some topics in jet propulsion like air compressors, right? And pump and hydraulic turbine. If you say, then I can add that problem in aerodynamic session itself. Okay. So I hope this session you like that session, and we will surely meet at Monday on 7 p.m. Okay. Thank you. Bye bye. And Harry, please keep on keep studying. You are a very good student. I personally feel that, especially Harry and one another person called HFYDD. I don't know what he's writing. Nikhil is also a very good student, and another one is Deepak. So these 3-4 students which I identified, they are very good, and if you people are worked well for upcoming 1 month, you are surely going to get a good rank. So I wish you all best for your exam, even though we are going to meet in the Monday, and hopefully everyone, like all of you, are going to get a good rank, and we'll surely meet after the GATE exam. Okay, thank you. Bye bye.